section 1.1, day 2. Today we're going to start our notes by talking about piecewise defined functions. And we have seen piecewise defined functions in different math courses before. What makes something a piecewise function is that there are different parts of the function that live on different parts of our graph, and where the function lives is defined by the domain part in the function. So what I'm talking about right now is this part right here, this if x is less than or equal to -1 or if x is greater than -1. So that tells me that the first function, x plus 2, is going to live on the left side of x equals -1, that vertical line, because it's for values of x that are less than or equal to -1. And then the second function, x squared, is going to live on the right side of -1, where values of x are greater than -1. So when I graph piecewise functions, just to make it easier on myself, I always put a highlighted vertical line where I know that I'm going to have that domain change between functions. So I'm going to put a highlighted yellow line right here at x equals -1 to help me with my graphing. Okay, now the first function that I'm going to graph is going to be the f of x equals x plus 2, which is like y equals x plus 2. That's just a, let's see, y equals x plus 2 is linear, right? It's going to make a straight line. And we've got our slope, m, is +1, and our b, or our y-intercept, is +2. But again, this only lives on the left side of -1, up to and including -1. So wherever it hits that line, we are going to have a closed circle at that point. So if I were to start with a y-intercept at 2, I'm going to put my pencil on 2, but understand that the function does not live on the right side of the yellow line. So I'm just going to have to work backwards until I hit the yellow line. So I put my pencil at 2. And then if my slope is +1, if I were moving in the right direction, I'd be going up 1, right 1, up 1, right 1. So moving in the left direction from my y-intercept of 2, I'm going to be going down 1, left 1. Well, as soon as I go down 1, left 1, I end up right here at that point. And since I know that x plus 2 is where x is less than or equal to -1, it's going to be a closed circle on that line. And then I just keep going. Down 1, left 1, down 1, left 1, down 1, left 1, so on and so forth. So this is what our function looks like on the left side of -1. On the right side of -1, we have y equals x squared. And y equals x squared is quadratic, which we know shape-wise makes a parabola. This doesn't have any transformation, so it's just your standard parabola with a vertex at 0, 0. So I know that I'm going to have a point right here on my parabola. And then the next point on the right-hand side would be over 1, up 1, okay? Or over 1, left 1. Now, technically, there would be an open circle around that closed circle right there on the line. But these two functions meet at the same point when x equals -1. So that's kind of special for this graph. And then if I go back to my vertex, and again, trying to make more points on the right-hand side, the next point would be I would go right 2, and then I'd go up 4, 1, 2, 3, 4. And again, these are just standard points on a parabola. The next point would be over 3, up 9. There. And I could keep going, but that's enough. Okay, so that's what the right side of my graph looks like. And again, you could make a table if you needed to, but it's just always easier to graph if you know what the basic parent functions look like, because then you can just sketch them quickly. Okay, so I've got my graph completed here. And now I can answer the questions above, which are asking me what is f of 0, what is f of -3, what is f of -1. So I could do this two ways. I could either use the graph that I've created to answer these questions, or if I didn't have a graph or they didn't ask me to make a graph, I could just choose the appropriate function based on the domain and the x value that they're asking me to plug in. For example, if they want me to find f of 0, well, if I'm just looking at the function, f of x equals 0 is greater than -1. So I would use the second equation, or I would use the x squared to figure out what f of 0 is. If I plug 0 into x squared, 0 squared is 0. So f of 0 would be 0. Now, if I look at my graph, if I look at where x is 0, what is the y value? It is 0, right? Because the point on the graph is 0, 0. Talking about this point right here is the point that we're looking at, right? F of negative 3, where does negative 3 live? Well, negative 3 is less than or equal to negative 1, so that's going to be on the left-hand side, or that's going to be the first function, the x plus 2. Negative 3 plus 2 gives me a value of negative 1. So I know f of negative 3 is negative 1. And that should match with my graph. If I find x is negative 3, and I look for that point on my graph right here, when x is negative 3, it's a little hard to see. There it is right there. The value of my graph is at negative 1. And then finally, f of negative 1, when x is negative 1, okay, and again, that's my highlighted line. That's where my domain changes. So then I have to use the x is less than or equal to negative 1 because x is negative 1. That's going to be my first function. Negative 1 plus 2 is positive 1. And again, if we look at where x is negative 1, the value of the graph, that's that shared point right there between the two functions at the height of positive 1. All right, so now we have another situation where we're going to have a piecewise function, but we have to write the function this time based on the information that they give us. So example 2 says, an electricity company charges its customers a base rate of $10 a month plus 6 cents per kilowatt hour for the first 1,200 kilowatt hours, and then 7 cents per kilowatt hour for all usage over 1,200 kilowatt hours. Express the monthly cost E as a function of the amount X of electricity used. And then they want us to graph the function. Well, we'll cheat a little bit on that part when we get to it. But first, let's write our equation. Okay, so whenever we're writing a function and we're representing some sort of a real-life scenario with a variable, we need to call the variable something. My favorite variable is X. So in this situation, I'm going to let X equal the number of kilowatt hours used, because that is what our monthly cost is going to depend on, is how many kilowatt hours we're using. So X would be our independent variable, right? And then the cost would be our dependent. So a couple pieces of information to kind of pull out of this problem. Up to X equals 1,200, the cost is the base rate plus $0.06 or 6 cents per kilowatt hour. So in equation form, if we think about just a linear model, it's going to be our base rate, which is $10 a month, plus then it's going to be 6 cents per kilowatt hour, so 0.06x. Okay. But then what happens when our usage is above 1,200? So for X greater than 1,200, our cost is the base rate plus, if we're using more than 1,200 kilowatt hours, then we have to pay for the 1,200. So plus 1,200 kilowatt hours at the 0.06 rate plus 0.07 times the kilowatt hours over 1,200. Okay, so in equation form, that is going to be our $10, our base rate, plus that 6 cents per hour, but we know we're over 1,200. So we know we're going to be paying 6 cents per hour times the 1,200 that we use, plus then it's going to be 0.07 times, and then whatever X is. So let's say X is 1,300 kilowatt hours. Well, remember, we're not paying 7 cents times the 1,300 kilowatt hours. We're paying whatever kilowatt hours it is more than 1,200. So this would be the 7 cents times our number of kilowatt hours, which is X, minus the 1,200, because we already paid for the 1,200 kilowatt hours at 6 cents per kilowatt hour. All right, so our third equation is a little bit complicated there. All right, and we can do a little bit of algebraic simplifying with this last one here. So let's take a look at what we can do to that equation. We've got 10 plus the 0.06 times 1,200. If we simplify that, we get 72 plus 0.07 times x is 0.07x. And then don't forget we're distributing right here, okay? And then 0.07 times 1,200 gives me 84. So minus 84, okay? So 10 plus 72 would be 82, and then 82 minus 84 would be a negative 2. So when we combine like terms here, we end up with 0.07x minus 2. Okay, so that is going to be the equation for x greater than 1,200. So we're ready to write our function over here. We'll call it E of x, okay? So the electricity cost is going to be equal to, and we know we have two pieces to our function. The first piece is that 10 plus 0.06x, and this is for values of x that are between 0 up to and including 1,200. And then the second part of our equation is the math that we just did to simplify. We could leave it in unsimplified form, but it's a lot easier to look at in simplified form. So that part of the equation is going to be 0.07x minus 2, and that is for values of x that are greater than 1,200. Okay, and if it bothers you that I wrote the first equation with the y-intercept first and the slope second, and then the second equation with the slope first and the y-intercept second, don't be bothered by that. You can certainly change it around. It doesn't matter. All right, so now we're supposed to sketch a graph of what this is going to look like. So I'm going to just make a little, and we're not going to fuss about making this perfect here. I'm just going to make a little XY axis here. We're all in the first quadrant, so we don't really have to worry about it. And we know that our x values are in kilowatt hours, and we know that our y values are going to be our cost in dollars. And we know that that kind of yellow line that we talk about, the highlighted line where our domain changes, so I'm just going to draw it like right there. Okay, that is happening at 1,200 kilowatt hours. So right here on my graph, I'm going to say that this point is 1,200 kilowatt hours. And I know that my first equation is going to live on the left side of that line, and my second equation is going to live on the right side of that line. And I know that my first equation, the 10 plus 0.06x, has a y-intercept of 10. So I'm just going to say right here, this is 10, okay? And it's a linear function, so it's going to make a straight line. And I know that this point right here where my two functions both hit that x equals 1,200, it's going to be a shared point. For the first line, it's going to be included because our first function is for values of x that are between 0 and 1,200 and include 1,200. So this is a closed circle for the first line. The second line is for values of x that are greater than 1,200. So the open circle and the closed circle are lying right on top of each other. And then the slope here is 0.07, which is slightly larger than 0.06. So we're going to exaggerate this a little bit on our graph. And we know that, so it's going to have a little bit greater slope, and it's just going to continue on. So this is what I meant by when I said we're going to cheat a little when we make our graph. It's not perfect, but it shows what's going on with our function, that we have that shared point where our two costs intersect when x is 1,200, and that our slope is a little bit less on the left-hand side, a little bit greater on the right-hand side, but both of these functions are linear. All right, moving on to the next part. It says, in mathematics, we are often asked to rewrite mathematical formulas in terms of a single variable so that we can either maximize or minimize our function. Recall that for quadratic functions, maxes and mins always occur at our vertex, okay? So that's just kind of reminding you that when you're dealing with a parabola, remember when you're looking to maximize, you're always looking for that highest point if it's opening down, or if you're looking to minimize, you're looking for that lowest point if it's opening up, okay? But example 3 is not about a parabola. Example 3 says, express the area of an equilateral triangle as a function of the length of a side. First of all, this should be a familiar problem to you. This is a problem that we did several times last year in pre-calculus. All right, so we're going to start with taking a look at an equilateral triangle. And obviously the definition of equilateral is that all 3 sides are the same. So here's my equilateral triangle, and I am going to label the 3 sides of this triangle as x. You can call them whatever you want. I'm just going to call them x, okay? But we're supposed to express the area of this equilateral triangle as a function of the length of a side, which means that when we're done, we should have area equals and then something with just x as a variable, okay? So let's first make a notation here that x is the length of a side, right? And what I know about triangles is that the area formula for triangles is area is equal to 1/2 times the base of the triangle times the height of the triangle. And I already know that the base of my triangle is x, right? Because that's this distance right here. That's my base of my triangle. But what I need is an expression for the height of my triangle, which is this right here. This is the height of my triangle. I need an expression for that height in terms of x, and that's what makes this problem challenging. So let's write that down. We need to find an expression for h in terms of x. Okay. Well, when I look at my picture that I've drawn, what I know for sure is that when I drop that perpendicular line down to the base and I call it height, it creates a right triangle, right? And so if I were to now pull out that new triangle that I just created right here, where this side of my triangle is the height, and then the height obviously bisects that base in half. It might not look like that in my picture, but it does. So then I know that the base of this triangle would be 1/2 x, because it should be half the distance of the equilateral triangle. And I know that this side right here is this side right here, so that side is x. So I have a right triangle now, and I know that there's this relationship for the 3 sides of right triangles, the Pythagorean theorem, which is a squared plus b squared equals c squared, where a and b are the legs of the triangle and c is the hypotenuse. So I can use this relationship of the 3 sides of a right triangle to solve for h, because the other 2 sides of my triangle are already in terms of x. So then I will have an expression that will give me the height of my triangle in terms of x, and I will be able to plug it into my area formula back here, right? Because that's what I'm looking for, is something where I can plug what h is equal to, but in terms of x. So it doesn't really matter which side you call a and b, so I will say that a is h, so this is going to be h squared plus, and b will be the base, so 1/2 x squared is equal to the hypotenuse, which is x squared. And so now I do some simplifying. This is going to be h squared plus, when I square 1/2, I get 1/4, and then when I square x, I get x squared, and this is equal to x squared. So again, my job here is to get h alone. So h squared is going to be equal to x squared minus 1/4 x squared. Those are like terms. 1x squared minus 1/4 x squared would be 3/4 x squared. So h squared is equal to 3/4 x squared. And then if I just want h, I have to square root that entire thing. So I am square rooting the 3, the 4, and the x squared. So when I do that, I can't do anything with square root of 3. That's going to stay square root of 3. But square root of 4 will be 2 on the bottom, and square root of x squared will be x. So I have just come up with a formula for what h is equal to in terms of x. So now the last step in my problem is going to be to substitute that back into my area formula. So I have area equals 1/2 times my base, which is x, times my height, which is square root of 3 over 2 times x. And then I can simplify this. So area will be equal to, and again, if we just think of this as being all fractions and we multiply straight across the top, straight across the bottom, 1 times x times square root of 3 times x is just going to give me square root of 3 x squared. And then on the bottom, 2 times 1 times 2 times 1 is going to give me 4. So my area equation is going to be the square root of 3 x squared divided by 4. If a function f satisfies f of negative x is equal to f of x for every number x in its domain, then f is called an even function. And the geometric significance of an even function is that its graph is symmetric with respect to the y-axis. What that means for us is that the y-axis is like a mirror for the function. And if you covered up half of it and looked at it, the other half should be a mirror image over the y-axis. So if we know that a function is even, we can use that to use the symmetry of the graph to help us sketch the graph quickly if we're trying to make a picture of what our function looks like. So example 4 says, show that f of x is an even function and then use symmetry to sketch a graph. All right, so we've got two jobs here. Our first job is to show that f of x is even. And what that means is they want us to show that f of negative x is equal to f of x. That's how we show it or prove it algebraically. And basically what that means is f of negative x means that we are taking negative x and substituting it in for the variable wherever x appears. So f of negative x would be equal to 1 minus 3 times, and then we're going to put negative x in for x, and again, plus negative x to the 4th. And then we have to do a little bit of simplifying. So f of negative x would be equal to 1 minus 3. Now, negative x squared. We all know if we square something negative, it comes out positive. So this is just going to become x squared again. And the same thing with negative x quantity raised to the 4th power. We're multiplying negative x an even number of times. It's going to become positive x to the 4th. And look at that. F of negative x is 1 minus 3x squared plus x to the 4th, which is f of x, which is what we started with. Okay, so right there, we just showed that this function is an even function. Okay, that's the work that shows that. All right, so now to graph using symmetry, we're going to make a table of points. On the right side of the y-axis, and reflect them over the y-axis to get the left side. Okay, and you could just as easily pick some points on the left side, figure those out, and reflect them over to get the right side. It really doesn't matter. Okay, so if I'm going to just build a quick little table here, and I'm going to choose x values that are on the right side of the y-axis. So how about 0, 1, 2, 3. And I am just going to plug those into my f of x function. Okay, so you can do this in your head, you can do this on your calculator, it doesn't matter. We're just plugging some numbers in and getting some values of our function. So when x is 0, 1 minus 3 times 0 squared plus 0 to the 4th is going to give us 1. When we plug in 1 minus 3 times 1 squared, well, 1 squared is 1 times negative 3 is negative 3. So 1 minus 3, right now I'm at negative 2, plus 1 to the 4th is just 1. So negative 2 plus 1 is negative 1. And then I do the same thing with 2. When I plug 2 in, I get 5, and I do the same thing with 3. When I plug 3 in, I get 55. All right, so I have some points here that I can graph on the right side. When x is 0, my function is 1. When x is 1, my function is negative 1. When x is 2, my function is 5. And then, of course, when x is 3, my function is 55. That's way off the graph, right? So if I connect these, and I know it's just going to shoot up like that, I get something like that. So now to make the other side of my graph, I'm just going to reflect these points over. So obviously if it's on the y-axis, I can't reflect that point. That's right on that mirror line. But I'm going to have a point across from 1, negative 1. That's going to be at negative 1, negative 1. And I'm going to have a point across from 2, 5, which is going to be at negative 2, 5, right there. And so the other half of my graph is going to look like that. So you can see that it kind of makes a W shape. And you might want to make a note that quartic functions, this is quartic, it's 4th degree, quartic functions are W shape. Okay. All right, moving on. We just discussed functions that are even. What about functions that are odd? Well, the rule is that if a function f satisfies f of negative x equals negative f of x, that plugging in a negative x value changes all of the signs of the terms in the function to the opposite of what they were. That's what they're saying. Then f is called an odd function. And the geometric significance of this should say odd function, is that its graph is symmetric with respect to the origin. All right, so again, first thing we're going to do is algebraically, we are going to show that this is odd. So we are going to show that f of negative x gives us the opposite of our original function, gives us negative f of x. So when we plug in negative x, we get, let's see here, our function is negative x cubed minus 5 times negative x. And then we simplify this. Well, when you cube something negative, the result will be negative. So this term will become negative x cubed. And then negative 5 times negative x is going to make positive 5x, okay? And if I were to, since both my terms change sign here, I can show that if I factor out a negative sign, then inside the parentheses, I would have x cubed minus 5x. X cubed minus 5x is my original function, but now I've got this negative sign out in front that belongs to all of it. So I just showed that I end up with the opposite of my original function, all right? And so now if we're going to graph an odd function, to graph using symmetry, make a table of points. And again, I'm just going to say on the right side, but you could certainly do the left. And this is of the y-axis. But now here's the key. This is different. We are going to reflect over the x-axis and the y-axis to get the left side. Okay, so we're going to do exactly what we did in our last problem. We're going to make a table, choose a couple of x values, 0, 1, 2, and 3 always seem to work well. I am going to plug these into my function f of x and get my y values out. So when I plug in 0, I get 0. When I plug in 1, 1 cubed minus 5 times 1, that gives me negative 4. When I plug in 2, 2 cubed minus 5 times 2, that gives me negative 2. And when I plug in 3 cubed minus 5 times 3, that gives me a value of 12. All right, so then I go ahead and I plot these points. 0, 0, 1, negative 4, 2, negative 2, and 3, 12. Just way up there. Okay. So I have something that looks like that. All right, so now to make the other side of my graph, I'm just going to take each of these points and I'm going to reflect them over the y-axis and over the x-axis. So let's switch colors here and we'll just do this one point at a time. Obviously, 0, 0 stays exactly where it is because it's on that line of symmetry. Let's take a look at 1, negative 4. So if I reflect it over the x-axis, that would be 1, positive 4. And then if I reflect that over the y-axis, that would be negative 1, positive 4. So I end up with a point right there. Okay, then let's do our next point, which is 2, negative 2. So if I reflect that over the x-axis, 2, negative 2 would be at 2, positive 2. And then if I reflect that over the y-axis, that would become negative 2, positive 2. So right there. And then finally, my 3, 12. If I reflect that over the x-axis, would be at 3, negative 12. And then if I reflect that over the y-axis, would be at negative 3, negative 12. So right there. So the other half of my graph looks like that. Okay. Now, what I hope you're thinking about right now is the fact that f of x was a cubic function. And we know from Algebra 2 and from pre-calculus that cubic functions make this snake-like shape. Okay, so just a little note. Cubic functions are snake-shaped. All right. So our final examples for today, we're just going to get a little practice algebraically with determining if our functions are even, odd, or neither. The last two that we did, one was even, one was odd, but we haven't seen yet what a neither looks like. And basically a neither just looks like when you're done plugging in negative x for x and you do the simplifying, you don't end up with the exact same original function and you don't end up with the opposite function. You just end up with something else that's not either one of those things, and that would be a neither. All right, so my first example here, when we plug in negative x for x, in our numerator, we get negative x, and then in the denominator, we get negative x squared plus 1. All right, well, when we simplify this, we're going to get negative x over, and then in the bottom, when we square that negative x, we get x squared plus 1. Okay, so I want you to take note that there's just this one new negative sign. But this is a fraction. And remember, when we think about fractions, a negative sign anywhere makes the fraction negative, right? So we could actually write this as f of negative x is equal to negative 1 times x over x squared plus 1, right? That whole thing. That would be the same as putting the negative sign in the numerator. And so what we just discovered is that f of negative x is equal to negative f of x, which makes our first function odd. All right, in the second example, when we plug in negative x in the numerator, we get that, negative x squared, and in the denominator, negative x to the 4th plus 1. Well, when we simplify, the numerator is just going to go back to x squared because the power was even, and the denominator is just going to go back to x to the 4th plus 1 because the power is even. So we ended up with f of negative x gave us back f of x, and so we know that this function is an even function. The last example is a little bit tricky because they're throwing some absolute value at us. But we're going to do the same thing. F of negative x is equal to negative x times the absolute value of negative x. And now we need to simplify. Okay, so we end up with, in the front, negative x times the absolute value of negative x becomes x, right? Absolute is the same as the absolute value of x, which I could write this as -1 times x times the absolute value of x. So what we end up with is the opposite of what we started with. And that tells us that our function was odd. So again, we did not have a neither example here, but just keep in mind, neither means that you don't get what you started with and you don't get the opposite of what you started with. You just get something different.